Hello, everyone. How are you? So let's talk about random things, shall we? What is randomness? What does it mean that a number is random? Is the number 42 random? It's hard to fathom this without getting all, metaphysical and pondering upon the meaning of life, the universe, and everything. Yet, in ancient times, it wasn't bearded philosophers and mathematicians who asked these questions. It was gamblers, fortune tellers, and wizards, characters we normally associate with games. And as a game developer, randomness is of specific importance to me. So let's play a practical game to see how good we are at this, at defining randomness. Let's say we have a coin, tossed several times in a sequence. White is for heads, red is for tails. Now, one of these two series of tosses is random, and the other is not. Can you spot the random sequence? Let's have a vote. Who thinks the first sequence is random? Please raise your hand. All right. Who thinks the second sequence is random? Please raise your hand. Not so bad. OK, now this was a great party trick. I'll have you know that most of you are correct. The second sequence is really random. The first one is a complete fake. The first sequence was made up by a human, not by the coin. It so happens that humans, when asked to generate randomness, tend to alternate a lot. Say, when you try to enter a random string on your keyboard, you just turn into a keyboard cat, and you just keep banging your paws against alternate sides of the keyboard, right? And your fingers go like this. You don't just press the same key over and over again. And humans tend to do a lot of that switching back and forth. But you can call their bluff. And there's a probability formula for that, as you can see. So in 32 tosses, such as these, it is likely that you will get a sequence of 5 identical outcomes in a row. It is even more likely that you'll get 4. So in all likelihood, the first sequence out of these two is more suspicious when we apply this test. The thing with the human mind is that it searches for patterns everywhere, even when there isn't one. It tries to fill in the gaps heuristically. People try to find meaning in meaningless sequences, as we all do when we reflect on events in our lives. Our idea of randomness is defective. Humans cannot reliably generate randomness, nor will they know a series that's random, even if it attacked them in broad daylight. If we can't reliably produce randomness, we rely on machines instead. But what are the devices that the machines can resort to? There are two paths that can be taken here. One is true randomness, and the other not so true, namely pseudo-randomness. Both perspectives have their own pros and cons, and depend on what kind of mechanism or stream is tapped into for generating random numbers. In essence, true random number generators use a very physical source to feed. That entropy which they plug into can be anything from background noise to radioactive decay to fluid motion. There used to be a random number generator that was based on recording lava lamps called LavaRand. The distribution is even, so each outcome is equally probable. And each successive number is completely independent of the previous ones. No number has any bearing on the rest. Pseudo-random number generators, on the other hand, rely on maths, using algorithms or functions that spit out random numbers and then recycle them in some way. the probabilities of generating given numbers are more or less equal depending on how advanced the algorithm is. Finally, they're not independent, which means that one generated number influences the fate of the next ones in a predictable way. We call that deterministic. And in this talk, we're trying to escape entropy. We're trying to get away from cryptography, and for us, determinism is a good thing, so we'll focus on the pseudo-random. First, let's tap into a simple pseudo-random number generator and ask it to generate some numbers for us. It all starts with a magic number called seed. Let's feed our generator with number 1 as the seed and see what random numbers it can churn out for us. Okay, thinking. There we go, random numbers coming out. All good. Let us now look under the hood. And indeed, there is a function that grabs this seed. It does some computations. Outputs the number it computed, and then it stores the state of that number and fills the gap with it again. Rinse and repeat until that number, see, is the same as the seed. Then the pattern will repeat. That would be the period of this function. So the next number is 8, and then 1, and then 5 again. The bottom line is that the seed allows us to generate the exact same sequence every time. Now, this was a terribly primitive generator, but gives you an idea of how prudent you must be with these for your applications. So you might want to select the technique of random number generation carefully. And that's where GameplayKit can come in that regard. And let's take a look at what it offers. For pseudo-random number generation algorithms, you can choose from 3 of those in the GK random source superclass. Here's a gist. First, there's one with an unspeakably awful name that I'm not even going to pronounce. But you already know it, in fact. If you look closely, you'll notice that that is the very same formula that we used under the hood in our previous example. However, here, the parameters will be sufficiently ginormous, so in practice, you won't encounter the problems of our primitive example. It does have a slight preference towards certain numbers, but it is fast. The Mersenne Twister is a more modern algorithm. Its period, so how many numbers it can generate in a sequence before it repeats itself, is larger than the number of particles in the observable universe by a few times. And it provides quality randomness, trust me. It is slightly slower, though. The familiar-sounding ARC4 source uses the well-known ARC4 algorithm and stands in neutral ground between speed and randomness. Overall, for simple simulations, really any of these is sufficiently random or random enough. But if you're into generating vast amounts of random numbers at once, it is good to know the ups and downs of each. Honorable mention goes to the convenience of shuffling. GameplayKit has a very, very handy method to take care of all that. Just rely on its shared random instance and call array by shuffling objects. Simple. Speaking of shuffling, interestingly, with one early iteration of the iPod, some users complained that their playlists weren't shuffled properly. So they would get the same songs or songs by the same artist played back to back. And that didn't feel random. In fact, it was really random, but it didn't fit their idea of randomness. So Steve Jobs made sure the algorithm was fixed to make it less random. So with more alternation, fewer streaks, kind of like the fake coin example that we saw earlier. One great way of curbing randomness and getting a grasp on it is distribution. which is the layout of all possible values and their probabilities. GameplayKit offers 3 out-of-the-box distributions we can apply to one of our random sources. The best known one is, of course, the Gaussian distribution, the famous bell curve, also known as the normal distribution, where the average values are the most common and those in the extremes are the rarest. So let's use our Gaussian distribution over dice rolls. Notice the super cool convenience initializer for a 6-sided die there. If we roll the die, say, 6 times, these are the example outcomes in a sequence. So you get the mid-range numbers, like 3 and 4, with the highest probability of occurrence. The shuffle distribution, also called fair distribution, is uniform, so any value is equally likely to occur, but it avoids using the same values in a sequence. It completely avoids streaks, so it'll try to exhaust all possibilities before repeating any number. And this example shows it quite well. Finally, the random distribution, which is the default, the basic superclass, uses simply the uniform distribution, so all numbers have an equal chance of being rolled, such as this. And that is all there is to it. However, for our considerations for many apps and games, you might want to pick the right distribution, not necessarily the default one. And here's why. Look at these raccoons, grown to completely random heights. I mean, whatever they were eating, it must have been radioactive. The variation in the complexity of life is never completely random, but in fact predictable, even the general height of raccoons. The way to make these randomized raccoon sizes look more natural is by spreading them over the Gaussian distribution. So only a select few will be abnormally huge or super short. Yet, this idea, importantly, applies to so much more than just physical characteristics. Okay, take a UFO invasion over this forsaken village. If we apply pure randomness, some ships will be in lockstep, moving together precisely on point, such as these 3 guys there. And this is not an air show, nor an exercise. Invasion is serious business. So with Gaussian distribution, their speed is random, yet more elastic. So you'll see less lockstepping. The units will fly more gracefully. There'll be a leader and some aliens lagging behind, but their average speed will be maintained. Still, regardless of probabilistic distribution, the randomly generated numbers are too random to create content themselves, to become content directly. Look at these numbers connected. I mean, it's a complete white plunging noise. It's rugged and rough, a complete mess. Now, wouldn't it be nice to have random numbers that form a continuum that makes sense, to infuse them with memory so that values have consequence, bear relation to the next ones in smooth transitions instead of these chaotic spikes? This need is fulfilled by procedural noise, where the random sequence is sleek and coherent, where it unravels controllably, where it's consistent, offers some degree of familiarity. So instead of white noise, you get velvet. That's random, yet organic. Now, the mother of coherent noise is Perlin Noise. It was invented by Ken Perlin in the 1980s while he was working on the CGI for the movie Tron. Now, this brought Perlin an Academy Award for technical achievement as late as 1997, because originally the Academy had disqualified Tron because they thought the use of computers in graphics was cheating. Okay. So, in a nutshell, a noise function is nothing else but a seeded random number generator, but the values are interpolated to make it smooth. And then the smooth functions are added on top of each other to create coherent, fractal noise. So let's take a look at raw Perlin noise and its example uses. Think of it this way. Perlin noise in one dimension is like a mountain range or a wave, something undulating. The use case for one-dimensional Perlin noise is anything wobbly, such as hand-drawn lines of a shaky hand on the right there. Two-dimensional Perlin noise is commonly used for texture generation, because it can be easily scaled and transformed. You can just grab a simple color gradient and have your machine churn out naturally looking textures. Perlin noise can span over 3 and more dimensions. You can use that to generate Minecraft-like terrained worlds with hills and caves and whatnot. Let's go into the rabbit hole and check out GameplayKit's built-in noise sources that will be available starting with iOS 10. The selection is a real cliffhanger, so let's take a look at a few of these. So, how do you generate such noise with GameplayKit exactly? First, you initialize a noise source, choosing the general style of noise, Perlin in this case. Now, this is the very noise generation algorithm whose parameters you can tweak. Then you feed this abstract source into a noise object, which would be its actual representation. Keep in mind that the noise source generates a field of values that's practically infinite in 3 dimensions, and that's what the noise object embodies. The noise source, the algorithm, can then be tailored by setting several properties. For Perlin, one of these would be octave count, which is how many successive noise functions with higher frequencies you want on top of one another, increasing the level of complexity and turning Perlin noise into a fractal. Or frequency itself, which controls the number of visible features. So if we set up Perlin noise generation algorithm accordingly, we can create a pretty looking texture that's kind of infinite in extent. And no need for trial and error here, because these also happen to be the default values, so you don't even have to set that. Now, the noise source generates values between -1 and 1, which makes it so scalable. So when creating a noise object, you simply point these values to some colors, creating a noise gradient. Then you sample a slice of the noise to create a noise map, like grabbing a cheese slice from a block of cheese, and you put it in a texture. And that's how we get a real cloud texture, like the one you see in the background, in just a few lines. On a side note, you can not only tinker with source parameters, but the noise object itself is easily transformable. You can use numerous translations to change its character. You can invert, recalculate, add noises, apply turbulence, move, scale, rotate, and more. Okay, now let's see some action with what we've generated so far. One great application is animation. In this example, the noise map samples a slightly further region of the noise object with each frame, creating an animation of moving clouds. This can go on and on indefinitely without taking up much memory and without storing any textures anywhere beforehand. Better yet, if we move through the very noise object, cutting down through it, slicing deeper with each frame, you'll get an animation of billowing and dissipation. So here I'm using 2 mirrored sprites, retexturing them as we go through the noise to create an infinite ink blot test effect. Importantly, Perlin noise does not only apply to visual representations, but can be hooked up to almost anything. After all, it's just a field of numbers. So maybe movement. Here I'm sampling noise values to drive the zoomed camera for a shaky hand effect. If you put in completely random values there instead of coherent noise, you'll just get nonsense. The camera would be just all over the place. Okay, how about a creepy cyberpunk vaporwave avatar and his minute facial expressions as another application? The different Perlin noise instances there have their values hooked up continuously to facial muscles, making this even creepier and more uncanny than if it were simply randomized. But there are other styles of noise in GameplayKit, such as the ridged noise source, which is like Perlin, but with more spiky peaks, good for generating Himalayan mountain ranges, or electricity, or spells, or cheesy fire, because we can. With some simple tweaks, I also created stone and marble textures. The Voronoi noise is interesting. It's botanical, organic. You can create cool cellular worlds or cracked crystalline structures. Or the cylinder noise. I just applied a little turbulence to generate a natural-looking texture of wood. This could go on and on endlessly, like the noise itself. So let's use everything at once to make something cool. Here's a final example of different noise types applied to generated textures of water, sand, tree-covered hills, and mountain peaks. These noise objects can be combined creatively on a much grander scale. I've mapped them to a ridged noise source here, so that the lowest values are textured with water, and these biomes continue all the way up until the mountain peaks. The noise objects are really lightweight, so why not use them to texturize a prototype of an entire planet? The nature of random coherent noise is perhaps best visible when it's mapped to a 3D terrain geometry object in SceneKit, for example. So here you have a visualization of the relatively smooth Perlin and the more peaky ridged noise and how lucid they are. Pure randomness would just be completely illogical. But why limit yourself to a planet when you can make something of more magnitude, such as a procedurally generated universe around the player in your game? The procedural generation of textures and terrain stems from the old-school demo scene, where they packed huge worlds into tiny executables. These worlds, generated by coherent noise, are random, yet deterministic. This means you can create a multitude of familiar-looking textures, surfaces, or other random pieces of art at runtime. Still, that procedural noise is in fact a seeded pseudo-random number generator inside, just like the one I presented at the beginning of this talk. So using the same seed property value, you'll be able to recreate the exact same sequence. So one number will be able to conjure up the same world or the same universe for your player. Randomness is indeed a very subtle field, and using it in your apps can be tricky. Whatever you generate, it may be too random or not random enough. Einstein himself had a bit of a problem with this in his famous saying, God does not play dice with the universe. And indeed, much of our world can be only understood through the principles and patterns of randomness. And I hope I've managed to make you question your perception of it. I encourage you to try and control it. impossible in life, so at least maybe in your apps and games, and make the previously white noise coherent and intelligible using the right tools, such as GameplayKit and iOS 10. Thank you very much for having me, and enjoy TrySwift.